Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel CAD CA Master. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. Yep, well, in this session I'll be taking you through the basics of finite element methods. This is the second video which I'm creating on basics of FEM. You can even refer the first one. Well, the agenda here is to deal with the general governing equations, and then we'll see the direct method, variational methods, and the Galerkin weighted residual technique, and the weak forms, and finally we'll have a look into the equilibrium equations and we'll see the problem as well. Well, let me just start with this. I would like to take the pen. Yeah, so the first thing, if you're going to deal with the finite element method process, what exactly we do in the beginning. So first thing, we take up the model. Okay, this is the rectangular plate. We define the material properties, likewise Young's modulus, Poisson's ratio, density. If you're going to consider the mass predictions and all, we can just add this one. Yeah. Next, we take the boundary conditions and we define it as per the requirement. Here we're gonna just define the fixtures. With respect to here, we're gonna apply the load. Yeah. And then after this, we're gonna just discretize the model in the form of the mesh, where we can see the quad elements. Okay, and then we're gonna take this into account, and then we're gonna just create the shape functions on this by using the interpolation functions. We solve them, and finally we form the stiffness matrix. We'll see that as well in the later session. Yep, so you could see with this we have the individual elements as a free shape functions. Then here we just do the calculations for each and every element. So where we solve the Galerkins residual function. Okay, we call it as residual function here for each shape functions. This is the shape function here, and then we form the stiffness matrix for each element, and then we combine these all to form a global stiffness matrices. Okay, so here if you could able to see, if you consider this element here, so we call it in short as a shape function. For this one, we have the nodes. On this particular nodes, we gonna extract the results by solving the residual function. Yeah. The next comes is to deal with the partial differential equation, that is F, which is equal to stiffness matrix into displacement. Yeah. So what exactly it does is it combines all the stiffness matrices here and it solves for this by using the programs like ANSYS and other, and then you're gonna get the results in the form of the displacement. Okay, and then this will be taken to derive the stress and strain values, and then you could see, so finally we're gonna get the results in the form of the displacement for the entire domain, and with respect to this we're gonna obtain the stress, strain, FOS with this. So I hope this particular process is complete and it is explainable for you guys. So now at the back end, what is going to happen, so how this particular residual functions will be solved and how it is derived, we'll see. So now this particular entire method, we call it as divide and conquer rule. So where we just discretize the entire model into small segments. So this might be 1D, 2D and 3D elements. Right now it's a 2D element. We can even take the trias. Here we have the quad. Well, next we'll see the general governing equations. Everyone can ask me, so in the beginning, so how exactly these all the derivatives are considered into the FEM, and then how we gonna consider the best one for our analysis. So how it has been chosen for the latest programs, right? So to answer this question, so we have the three methods in the earlier days. So one is the direct method, and then we have the variational method, and we have the Galerkins Weighted Residual Method. Now we'll see how these are going to help us. The first one is the direct method. So what it does, so we call this particular direct method as a strong form. Okay, so this is the equation ei by 4 derivative of ux by dx, which is equal to q of x, plus adding all the boundary conditions into account. So this particular equation is known as the strong form, and the disadvantage of this one is it will only help us to solve the simple matrix of the axial beam problem. So it has some limitations to deal with the complex problems, so we don't use this one for the complex problems. I hope it's clear. Yeah, so we know these are the differential equations. Yeah. So now next one is the variational method. So what exactly here happens is before that, this variational method and the Galerkins weighted residual method, these both are known as the weak forms. So why we call it as weak forms? Because they form the integral form. So these are the integral forms. So with this, we can able to easily solve the stiffness matrices and form the approximate results. Not exactly 100% accurate, so that you need to remember. So every FEA results you're gonna get it, it's not accurate. So it's just approximate solutions. Yeah, so this is what I have told. So these are the approximate solutions for the equilibrium solutions. So by using this weak forms, we derive them. So what is the main advantage of this is they are easy to solve. Well, now we'll see with respect to the variational method what exactly is going to happen here. So when it comes to this variational method, this particular method works on the principle of minimum potential energy. So what it does mean, we'll see. So if you're going to deal with the potential energy, it takes strain energy and the work potential into account. In short, this is the equation, so that I'll show you again. So potential energy equal to strain energy plus work potential. So here, when it comes to strain energy, the deformation energy stored in the structure, and then the work potential is the negative of the work done by the external forces when the potential energy is in terms of displacement. Means to stop this one, and then we minimize this potential energy with respect to the displacement. Well, so this is all about this variation method. So equation you could see, so total energy which is equal to strain energy plus the potential energy of the external loads. Yeah, so here again this particular variational method, it is not that popular, and we use it for again simple P models and all. So now when it comes to the Galerkin Weighted Residual Method, what exactly it does is, so this particular method is a very powerful method, okay, and it will help us to find out the approximate solution for all the kinds of differential equations. So here we do the piecewise trail function approximation for the weak form of the weighted residual technique, so which forms the basis of finite element method. So this particular method we use everywhere at the time. So if someone asks for this one, so which is the equation, we use it. So we get it as Galerkin Weighted Residual Method we implement to solve the stiffness matrices at the back end in the algorithms. Well, so here we're gonna generate the weak forms, and we use piecewise trail functions to approximate the concepts. Now let us just consider a simple problem. So you can see this is the rectangular plate which just had showed it, right? So here we consider this is the boundary where I've just highlighted as with the red, and this is the region we take it as a domain. Okay, these are the symbols for that. So now in general, if we consider this particular general problem of engineering analysis described in the form of the differential equations, so if we consider only the domain, this is the domain, valid domain for this one. So the boundary conditions, if we consider this one, okay, for this region, so these are some assumptions we do it, and we try to solve the stiffness matrices there. The first thing is we assume the trail solution to the problem. So if it is a one-dimensional problem, we may choose the trail solution as this one. So we call it as polynomial equation. So where we have the C0, C1x and C2x square and C3x cube, like this it will keep on going. Yeah. Whatever this function is there, it won't satisfy the differential equations and the boundary condition. Okay. So what we do here is we substitute the assumed function, that is weighting factor we call it, to find out the error. Okay, so this is going to help us a lot to tackle this weighted residual method. Now here with this we try to determine the unknowns, that is C1, C2, C0, C3 and all, in this particular assumed trail function in such a way that to make these residuals as low as possible. So yeah, so now we'll see how exactly this particular equations are formed. Now when it comes to this equation, so in general the statement you could see here, if we consider any of the unknown field variable u, and if you would like to approximate the solution of the form, so this is the equation where we have the u. So if we consider u hat for a certain value I, and which is equal to phi summation from I1 to n, ci and I is the equation. So if we consider this one, so here we have the ci is the independent coefficient which we need to find it out, right? C0, C1, C2, C3 and all. So which is to be determined by the weighted residual process, where we're gonna just define the weighting factor and try to just set it to 0 and just find out all these C1, C2 values, the coefficients, and the function ni, these two, the weighted process and the ni, the function ni, we keep it as pre-selected because these will help us to satisfy all the boundary conditions. Okay, where we consider RD as XYZ as a domain residual. So this is the domain residual. So if we consider these things into account, the equation will be rewritten as this. Yeah. So where we have the WI is the weighting factor, RD is the domain residual. Yeah. And then this is the equation. So integral form. Now we have the WI which is equal to NI. And yeah, so this will satisfy the weighted residual equation, which help us to bring it back to 0 everywhere in the differential equations. By that, we're gonna get the displacement value in the governing equations. Let's see now how do we derive it. So in the weak form, what exactly we do, we form the integral functions, we do the integrations, and which will help us to reduce the continuity requirement in the trail functions. Okay, so here if we consider the equation, this is the equation. So where we have the initial boundary condition set to u and the weighted residual set to 0, this equation will be formed. So if you would like to have the derivations and all, if you would like to just go through that, you can just refer P. Sheshu, one of the book which I have referred it. Yeah, so here if you consider the equation, that is differential equation, so for the axial loading condition, this is area into Young's modulus, the derivative of u plus q is the loading condition, which is equal to 0. Okay, with respect to this, if you would like to rewrite the equation, this is the form where we have the u hat is the exact solution which we are looking for. So this is the one. So where Wx is the weighting factor, that is weighting function we consider, and then we have the PL. So this is again weighting function with respect to the boundary condition, and these are the known boundary conditions, that is PL. Okay, and then here we have the Q is the loading conditions, that is loading intensity. Now this is just an optional for you guys, so sometimes you might find this kind of equations where we have the AX and some other things. So this will be formed with respect to the requirement. Let's say we have the axial loading condition, we take it as direct loading point. So if we have the varying load conditions, that is linearly varying load conditions, we consider this one AX, which is equal to A into X. Okay, along the length we define the load. Now if we consider the same model which we were working on, so if I take an element as a shape function and this is the node, so on these nodes there are the quad elements, right? So here these are the 4 nodes. On these nodes we try to simplify it. Let's say if I consider u hat of xy and try to explain this particular scenario, it might confuse you. So what we do is we just simplify this particular equation into ui, which is equal to all the nodes 1, 2, 3, 4. Here if it is a 2D model, if you are not going to consider into the 3D environment, only the 2D if you are going to consider, so axial loading and all, so in that case we have only 3 degrees of freedom for each and every node, 3 translation, no rotation. Yeah, so with respect to that we can just get u1 u2 u3 u4 displacements. So now if you would like to just form an equation, so you can just write it down like this, n1, this is the formula. So in short you can just add the summation uy, that is ni, we can just write it out. Yeah, so now with this we're gonna form the shape function by including the boundary conditions and weighting factor into the equation. So where we take the weak form, yeah, so these all the values will be substituted here in this one. Okay, so all this one we substitute these and we find out unknown values C1, C2, C3, and then we directly put these into the stiffness matrix. Sorry, this is the stiffness matrix. This is the displacement, and then we get the results. So this is overall process in short. So we just take the shape functions into account, and then on the shape function on each and every node we try to just get the results by utilizing the weak forms, where we just use these formula and then we get the results, and then the stiffness matrix will be solved for particular element, and we do the same for all the elements, and we just form a global stiffness matrix. Yeah, this is clear. And then next I would like to take you through a simple a problem example. So how we gonna just derive this equation? So we have just seen this one, right? Differentiation like derivative of this one, that is a plus q, which is equal to 0. How we gonna just land up with this equation? So if we consider this scenario, in order to solve the stiffness matrix, the problem here explained. So if I consider this scenario where I'm going to just apply the axial loads along x and x plus delta x direction, this is the overall length L, and we have the displacements u1 and u2 and the loading condition. Yeah, if you are going to just derive this one, we'll start with the Hooke's law. We know Hooke's law is stress by strain, which is equal to Young's modulus, E, which is equal to stress by strain. If you would like to find out the stress, we have the loading P divided by area, load per unit area. And then if you would like to derive the strain, change in length to the original length. And if you would like to have the stress, Young's modulus into strain. Okay, so just considering these all the things, if you would like to rewrite the equation to get the change in length, so this is what we are looking for. So equation P, which is equal to here, that is stress into area, where we have the stress which is equal to Young's modulus into strain. We write it where we just keep A like this, and we have the E, where E we just write it out, chain derivative of u by ux, and which is written as u2 minus u1 by L. So now if you would like to find out this delta u, so what exactly equation we have it, that is PL. If we rewrite this equation divided by, this goes down AE. So now let's say if you have a problem, just imagine, okay, and we have the axial load which is fixed here, and I have applied a certain load here. Yeah, so now if you would like to find out a change in length, if you have this original length, so in this case what we're gonna do, we use these all the inputs. So load, the total length, area into Young's modulus, you're gonna achieve this one, and then with this you're gonna just try to find out the strain, change in length to the original length, and then with this you gonna try to have the stress value, and then stress strains are there with respect to this displacement. This is what happens at the back end in the algorithm of any software. Yeah, now we get back to this one here. So let's say if you would like to derive this one, so the first one, the loading condition, if you just try to solve it, this is along positive direction, we keep it as P of x plus delta x. So this is going towards negative direction, loading condition, so I write it as minus P of x, yeah, plus this is the integration of force into dx. Okay, then this is the integral of f, and then if you try to solve it, we just take the same thing here, minus P of x, we just write it as f into delta x, where we take the initial boundary condition as 0. Yeah, so if we limit this one, so try to just solve this and try to take the p loading outside, and then you write it, and then once you just uh, simplify this one, you're gonna have the derivative of p with respect to dx plus f, and then here we know this p here, the value of p is here, that is ae into du by dx plus f, and finally you're gonna achieve this equation. So now let's say you have all the values. Let's imagine if you would like to, if you need to find out Young's modulus, you have the strain value, stress value. So by using the formula, that is Young's modulus, which is equal to stress by strain. Put this with respect to Hooke's law, and just 15 ones are 15 twos are. You'll end up with the same value, 200 gigapascal. Right? So this is just a simple example for you guys to understand the basics when it comes to solving this in the form of 1D elements. So if you refer the P. Sheshu book, so they have derived each and every equations with respect to axial loadings and uniformly varying loadings and the heat transfers. So everything you can able to refer it there with respect to 1D, 2D and 3D elements. And then the same thing, the next one what I'm showing is the general equilibrium equations. This also you can find it, and with respect to derivatives by using the spring constants and considering the dynamic environments, how they have derived it, these equations you can able to get it there. So this book is very helpful for you guys, you can refer that. Now in short, I'll just show you the equation so that you can just remember, and later on you can utilize it. So when it comes to the general equilibrium equation, we have this equation mu double dot, that is P in the sense C damping u dot plus Ku, which is equal to P of T. So this is the equation. Yeah. So where we have M is the mass matrix. Yeah, and then we have P, which is C known as damping matrix, and K is the stiffness matrix we already know. Yeah. And then here u double dot is the acceleration vector, and u dot is the velocity, u is the displacement, and this is the applied load. Yeah, so this is the description of this formula. Now when it comes to static analysis, we are not going to consider the acceleration and the velocity into account. We don't take the dampings into account and the mass matrix into account. We only consider the stiffness matrix and the loading, because in the static conditions we don't have these all the things. Yeah, so now when it comes to buckling, we have this formula where we can just utilize this one and try to solve the buckling problems. And when it comes to vibration and modal analysis, we try to extract the results with this one, where stiffness matrix minus eigen value into the mass matrix into phi, that is eigenvector, which is equal to 0. With respect to this, you're gonna get the natural frequencies and the mode shapes. So yeah. And then we have the frequency and the transient response analysis if you would like to do. This is the formula we take into account. Just semester of this. So this is all about the equations and the basics of finite element methods, which I could able to explain it so far. So yeah, so where we have just gone through the minor details which the fresher need to know about. Yep. So now simply just to conclude, we have just gone through the governing equations, the direct method, variational method, and the Galerkins weighted residual method. Yeah, and then we had seen the weak forms, how it is helpful, and what it does exactly is like at the back end it will at the back end it try to provide the integrations to the weighted residual functions, and it try to simplify them and try to give the approximate results for the equations. And then we had seen a problem and the general equilibrium equations. Well, if you would like to become a CA engineer, if you're a fresher or if you're an experienced person, so if you'd like to get trained with respect to ANSA, Hypermesh, Abacus, any of the tools, and if you'd like to learn somewhat, or you have some questions, or if support is needed, you try to contact us anytime. So these are the contact details below. Yep. So that's all from this session. We heartily thank you all for watching this video. If you enjoyed this video, don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn, and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.